All right. So yeah, this third one here, because of this negative exponent, technically that's like 3 to the negative 1 to the x. This is why we had to learn about decomposition, or how do you rewrite exponents in different ways. This is one of those rewrites. Well, 3 to the negative 1 power is a fraction, 1/3 to the x. This is decay. This is decay. So whenever you have a base to a negative power and it turns into a fraction like that, yeah, it's going to be decay. Let's talk about rewriting that number 2. So if I rewrote it, if I made this 4 to the negative 1 power, this would be to a positive x minus 1 power. You'd have to take a negative 1 out of that binomial, which would still be okay. But now we have 1/4 here, which is also decay. It's decaying. So now that we realize, hey, wait a second, this turned into a fraction because of the negative exponent. This, number 1, is actually also decay. Number 1 is decay because it's 1/2. We could rewrite that as 2 to the negative 1 power raised to the x, which would also be 2 to the negative x power. Ooh, so then good point. So number 4, not here, sorry. Okay. So number 4 is actually our only growth, only growth out of these guys, because yeah, that numerator is not a 1. It's so 3/2. What are you going to say, Josh?
I was going to ask for like number 1, is it decay, like for the fraction of the numerator is smaller than the denominator? Is that one like?
Yeah. So when the numerator is smaller than the denominator, you're going to be decaying. When the numerator is bigger than the denominator, you're going to be growing. So this is growth. We also call that as whenever you're less than 1 or whenever you're bigger than 1. Okay? And you can't ever equal 1. And we'll talk about that today. What about this? Does this look like growth or decay, Mason? How do you know?
Because as the x gets higher, the y gets lower.
Okay, so here's what he's saying. As x gets higher, the y's get lower. Decay. So today is all about exponential growth and decay. We're going to learn them at the same time. Because I'm not going to test you over, do you know if something's growing or decaying? I think we get it now. After that little bit of warm-up, growing as x gets bigger, y's also get bigger. Decaying as x gets bigger, y's will be getting smaller. I'm going to go through this example of, okay, an exponential function involves the expression b to the x, where the base b is a positive number other than 1. I'll show you in just a moment. But here are some examples of what we're going to see. Right? That's what we had. Y equals something. Like y equals 2 to the x. Y equals 3 to the x. We had that in warm-up. You could also have coefficients. You could have stuff hanging out, being added or subtracted out here. Because like what's happening to the inputs? What's happening to the outputs? You're going to hear me say that again today. But this is not an example of what we're going to talk. Notice how it says the base b has to be a positive number other than 1. Why would we not want that? It's negative. The parent function exponential graph for a base 2. You actually already have this down because I have full faith that you can put this in your calculator. 2 caret negative 3. 2 caret negative 2 and so on. So I'm providing you with what that regular t-chart would look like and what its graph would look like. Because I have full confidence that you can do this on your own. What we need to do is figure out the characteristics. What are the characteristics of this graph? Because I don't think we have it down. Key characteristics. Notice the flat line. It eventually gets flat over to the left in a growth. So any growth, we're going to say, has a horizontal asymptote. So horizontal asymptote in a parent graph, we're going to keep track of this. It's going to be 0. So that left portion of this graph, the horizontal asymptote is y equals 0. So notice how this says y equals, that's the outputs. Outputs equal 0. So if the outputs, for some reason, if I had 2 to the x and then there was like a -1 out here in this equation, then that means, okay, then this would be affected to -1. All right, there's another thing I want us to circle, and that's the y-intercept. The y-intercept is 0, 1. If I plugged in a 0, the output is 1. We're probably going to plug these 3 groups in because it's easy to plug in -1, probably mentally. It's easy to plug in 1 mentally. But it's the easiest to plug 0 in because anything to a 0 power is 1. So we've got horizontal asymptote. That's something that's going to be key every single time. A y-intercept, and then maybe I need to just plug in -1 and 1. And keep this shape. Keep this cashew shape. It extends in both directions. There's arrows on both ends. Let's put in arrows on both ends. Domain. Domain is all real numbers. Range. Well, it gets cut off because of that asymptote. Range is all real numbers as long as the outputs are bigger than or equal to 0. Sorry, there's an equal to symbol here. There's an equal to symbol, so it's greater than... That's my bad. Let me put that a little higher so you can see it. What if I just compare these functions? So, what we're looking for is, I'm telling you that the one on the left is the table from the parent function. So the one on the left is the parent function. You've got to figure out what happens going from the left to the right, from the inputs, and then what happens to the left to the right on the outputs. We're trying to discover what happens to this equation. So if this is the equation, what's going on from the table? So we are dividing by 3. So sorry, I cut somebody off. What? Huh? Multiply by 1/3. So we could either divide by 3, but you're going to see me write it as multiplying by 1/3 instead. So this equation is no longer y equals 2 to the x. It's actually y equals 1/3 times 2 to the x. That's how we're going to see these leading coefficients. So it's affecting the outputs. Notice how it's outside our function. Our function now is what is in purple up here. And it's affecting outside the function, so it affects the outputs. We're multiplying by 1/3. And notice what happens to the graph. You see the graph. You see the graphs, the comparison in the graphs. We've got to figure out what changes. So horizontal asymptote did not change because, well, what happened to the outputs? Oh, it's multiplied by 1/3. If you took 0 times 1/3, it stays 0. All right. We also want to make a note of the y-intercept. Notice where the y-intercept is now. It's no longer at 1. It's now at 1/3. So those are the 2 key parts. The y-intercept changed to 1/3. You don't have room for this slide. I took it out because I wanted to just stress how the first function was 2 to the x. The second function was 1/3 times 2 to the x. We're going to go through this journey again. Going through this journey again. Question?
So if you had 2 to the x over 3, you wouldn't count that as right?
Okay, so question was, if I had 2 to the x over 3, would I count that as right? I would be okay with that, as long as it looks like this, with f of x equals. That would be okay. Just know that on your homework, it looks like this. On your test, it looks like this. Or it may look like, I use a C dot. That's what it's called with Excel, or sorry, that's what it's called with Equation Editor. So you're going to see that form on the test and on probably on your study guide and so on. All right, let's go through another discovery. Compare the table. So nothing to the inputs, but the outputs are multiplied by 3. It'd probably be hard to start here at the top. That's why go to the y-intercept. 0, 1. See how that becomes affected. And then check it with the next integer. Okay, it still multiplies by 3. So that's what happens to the tables. That's what happens to the tables. And then you go to the graph. Go to the graph. Notice the difference in the graphs. So horizontal asymptote stays the same. There's that flat line. It stays the same. But now the y-intercept is 0, 3. That's the one thing that changed. So then what about the equations? Can you figure out the equation? So the parent function was 2 to the x, and we're taking 3 times 2 to the x. That's how the equation's affected. Let's go through another journey using those tables. New tables. You got to figure out what's happening. So, okay, obviously, again, the inputs are not affected. I will go over an example like that. Inputs are not affected, but the outputs, if you look at the y-intercept, how do you get from 1 to -2? How did you do that so fast? So we could either look at it as divide by -5, or multiply by -0.2. But what if I want to combine your thoughts? I want to combine your thoughts and multiply by a negative fraction. So I'm going to multiply by, I'll leave that for you. We're going to multiply by a negative fraction. So what happens when your leading coefficient is negative? That's where we're at. Let's see how it affects the graphs. It affects the graphs by, okay, this was our original parent function, and now what happens? Horizontal asymptote stayed the same, but then now y-intercept. 0, comma, it was -0.2. Do you know what that is as a fraction? What you got, James? -1/5. This is what I'm multiplying by. I'm going to multiply by that y-intercept. That's why it's so important to figure out what that y-intercept is, because that's going to be my leading coefficient. So if I want to know what is the original equation, if this is my parent function, and I figure out its t-chart using -3, -2, -1, 0, 1, 2, 3, I'll just multiply all the outputs by -1/5. See if you can do this one on your own. Look at the table. See what's happening. Look at the graphs. Is it legit? And then take a guess on what the original equation would have been. I feel like if we can go backwards, we could possibly go forwards. That's my little experiment with you. It's like a sick game I'm playing. On this one in the graph, you can't see the y-intercept. But just so you know, the y-intercept is definitely way past -2. It's supposed to be 0, -5, which is what we saw in that t-chart. So the equation, hopefully you took a good guess, but the equation turns into this. Okay, so this is just exponential functions with a base of 2. Just exponential functions with a base of 2. Graph passes through the point, 0, and then whatever that leading coefficient is. That's what we kind of discovered today. All right. The x-axis is basically the asymptote of the graph. That's that y = 0 line. The domain is all real numbers. Range is, oh, my bad. I put greater than or equal to 0. That's my bad. Can you look at this? The range is strictly positive. You can't actually ever equal 0. My bad. You're talking about the base. I'm talking about the outputs. you will never have an output in your column of 0 for this parent function. I also want to talk to you about what happens if we did a decay. What happens if we did a decay? If we did a decay, then 1/2 to the negative third power, that means it flips. So now we're at 2 to the third power, giving us 8. So decay could either look at 1/2 to the x or 2 to the negative x. I have full confidence in you that you know how to plug numbers in. All right. Exponential growth versus decay. I don't think you have this down, so here we go. Exponential growth versus decay. Similarities. So similarities, y-intercepts are going to be 0a, meaning that leading coefficient. That stays. The x-axis is the asymptote, unless you are affected outside of the main function. So the x-axis has the equation y equals 0. It's kind of like an oxymoron. X-axis that has the line y equals 0. Domain is all real numbers. That means we're going to have arrows on both the left and the right side no matter what. But the range is affected. So the only difference is the direction. That's it. The direction of the parent graph. Now if it has a negative leading coefficient, that's the leading coefficient. Like the parent graph, just the base to the power x, that parent graph is going to have two different directions. We talked about how one's going to be increasing the whole time, that's growth. One's going to be decreasing the whole time, that's decay. And then if you happen to have a negative leading coefficient, that has nothing to do whether you're growth or decay. Growth or decay is affected by only the base. What's going on with the base? Is it bigger than 1 or is it less than 1? Let's do, wait, strategy for, hold on, I can't remember. Oh. Well, here's, it says strategy for graphing these functions. If you want shortcut on your homework, plot the y-intercept, 0a, which is kind of, and then realize how, okay, so find the y-coordinate for the point containing the x-coordinate of 1. So like plug in 1. Basically, I'm telling you, do the t-chart for whatever the base is to the x power. Do the t-chart, plug in -1, 0, and 1. Figure out what these will be. And then see how you're going to be affected. Like, do you have something affecting the inputs? Do you have something affecting the outputs? Do we remember how the inputs get affected? Inputs are affected inversely of what we see. So if I see a minus h in the exponent or a plus h, then I do the inverse, meaning, okay, if I see subtract 1, I'm going to instead add 1 to my inputs. If I see a number being added onto the outside, then that means all my outputs will be added something on.
Is that 6x or b?
B's, these are B's for base. And then you plot this table, keeping the shape, keeping that cashew shape. If you have a plus k on the outside here, you've got to recognize that that'll also affect that asymptote. The asymptote may not always be 0.